the mystery of logarithms. You begin to become one of the people in the know what's a logarithm. There's a giant percentage of the population out there that doesn't know what a logarithm is. But you get to be in on the secret. Okay. This also, famous mathematician, although this is probably his most famous accomplishment, a guy by the name of John Napier in 1614 created the theory of logarithms, proved it all to be true. But he wasn't even a mathematician. He was a science guy. He was actually an astronomer. He was trying to work, measure distances to planets and how far stars are apart and all that stuff. So he's working with these really monster huge numbers. And he's going, this is horrible. No calculator realized. So if you want to multiply, even add, subtract these giant numbers, it's a real pain. So he was looking for a better system to deal with these giant numbers to make the computations easier. So he invented logarithms for that purpose. We've now found many, many, many other uses for them. But he was trying to make complicated calculations get much simpler. And when we get a little farther into this, I will show you how he had to do logs and how I had to do logs in high school, because you didn't afford a calculator with a log button on it at that point. And I want you to appreciate what all that calculator does for you and the tons of time it saves you. I can't tell you how much time that calculator is going to save you. But first we have to figure out what on earth is a log. So we started the other day with an exponential function. We put some limits on what size the base could be. What limits did we put on the size of the base? What kind of numbers? Yes, it had to be bigger than 0. And it can't be 1. Bigger than 0, it can't be 1. So why can't it just be greater than 1? Yeah, it can be all the decimals and fractions between 0 and 1. That's okay. Now I also need to point out then, base has to be positive. The exponent can be anything, because we know we can have positive powers, we know we can have negative powers. So x can be anything. It can be a real number. But will y turn out to be any real number? If you take a positive number to a power, what are you going to get? A positive. Even if you take a positive number to a negative power just drops it to the bottom of the fraction. It does not make the number negative. So if your base is positive, that means y is also always going to end up being a positive number. It can't end up being negative either. That's going to be important here in a little bit when we get a logarithm going. Okay. What Napier decided to do is he wanted to reverse this thing. At exponential functions, the numbers get really huge, goes up really fast. So he decided he wanted to find the inverse of an exponential function. So, okay, how do you find an inverse? Nope. Switch the x and y, there you go. You switch the x and y and then solve for which one? You solve for the y. So if you take, and I'm going to put a number in here instead of a b for base. I think you all work better with numbers. So if you take and say you have 5 to the x, if I say switch the x and the y, what's that going to say? X equals 5 to the y. But now when you're finding an inverse, you're supposed to solve for y. How do you solve for an exponent? How can I get that to y equals a number, equals something? It's not like I can move it to the other side. I can't isolate y. I can't get it by itself. It's up there in the exponent. I have no way to get it down. Well, if you're saying you want to put 5 under the x and make that 5 to the x, is that what you're trying to say? But if you do that, you'd have to do this as 5 to the 5 to the y. Because if you do what you do to one side, you have to do the other. Actually, what Napier did is he discovered there is no way to do it. So in mathematics, when you can't do something or you need some way to solve something, you develop a whole new theory and prove it to be true. So he went, okay, well, I want to solve for y. So to solve for y, I need to keep track of, though, what was the base and what was the number it was equal to. And I don't know the history of why he called it a logarithm. I don't know what logarithm means in Latin. I have a feeling it has something to do with base, exponent, something. But so he called it a logarithm, and he said we're going to keep track of the base. So the 5 is going to move down here and be a little base subscript. It's a subscript on your log. And then the number it was equal to goes inside. That's read log base 5 of x. So that's the log base 5 of x. And then he actually proved an entire theory on that this whole thing works. And all these rules I'm going to show you in the next few days are actually true. It's all been proven. Okay. We call that we're actually switching forms here. But to get you, let me give you a little more feel for it with numbers that you actually know. Would you all agree that 8 equals to the third power? Okay. I want you to write that as a logarithm. So, logarithms solve for the exponent. So therefore, it has to be 3 equals because you're solving for the exponent. So it's a log with what base? 2 is the base, so it'll be log base 2 of 8. So when you see a log, you need to think 2, think of the base. 2 to what power makes 8? 3. So if I was to give you log base 5 of 25, you would think 5 to what power makes 25? Yeah, 5 squared is 25, so the answer would be 2. Logarithms represent exponents. A log equals an exponent. Can't say that enough. Can't write that big enough. You're going to remember that forever. I'm sure this is on your journal. Logs represent exponents. It even gets bananas. That's crucial. A logarithm represents an exponent. When you see a log, think this is an exponent. Okay, let me have you try going another way. Let me kind of split that apart. Suppose I said, okay, this time I'm giving you a log base, what's a great base? Oh, log base 7 of 49 equals 2. Translate that back into an exponential statement. Change it back to something to a power. What would it say? The base is the base, so the base on the log is the base on the power. So 7 is the base. What's the exponent? What it's equal to is always the exponent. And so 7 squared equals 49. So this is always the base. This is always the exponent. You can keep that straight and you logs. Now, somewhere toward the bottom of your journal where I start asking you to just list rules and formulas, yeah, I ask you to show how you change from exponential form to logarithmic form. So you're going to want this in your notes. This is just the general formula. So if you have something in exponential form, we have your base to the x power. Finagle that around. How do you write it as a logarithm? X equals because you're solving for the exponent. Yeah. Yeah. Log base b of y. That's how you interchange between the two. Okay, what you're going to discover throughout this whole section, when we're working problems, we're actually solving equations and trying to solve for a variable. We look at the problem, and depending on what they gave us, sometimes the problem's easier to solve as in exponential form. Sometimes the problem's easier to solve in logarithmic form. So we're going to switch back and forth between the forms to get whichever makes our lives easiest. The other thing I want to point out here then, remember up here, when we started, we said the base had to be positive, and since it was positive, it forced y to be positive. That means down here on the log, if the base still has to be greater than 0 and it can't be 1, that means y also has to be greater than 0. So I always remember it, any number attached to a logarithm must be a positive number. You can't have a negative base. You can't have, this other number is called the argument. You can't have a negative argument. Every number attached to a logarithm must be positive. It can equal a negative number because that's the exponent, and you can have negative exponents. We've been doing those. But anything attached to the log has to be positive. You're going to have to check your answers when we start solving equations. You're going to have to check that you got positive answers. Okay, are we having fun yet? Are we having fun yet? Yes. Your enthusiasm is overwhelming. Well, we'll have some fun now. All right, I'm going to beat you to death with these. We're going to practice 15 million till we get it. All right, so if I said to you, I'm giving you the log base 9 of 81. With your brain, what would that equal? Why'd you say 2? That was lots of fast 2s. Yeah, you're saying 9, the base. 9 to what power makes 81? So yes, your answer would be 2. All right, what if I gave you log base 2 of 16? I'm saying 2 to what power makes 16? The answer would be 4. Okay. Well, if I give you nice easy numbers like that, it's pretty easy to think them. But I want to show you also another way you can get it if it's not such a nice number. If I had rewritten that 16 as 2 to the 4th power, where's the answer? It's in the exponent. Imagine that. The answer to a log problem is an exponent. Could it be? Oh yeah, always. So, but what has to happen, if your base on your log is 2, the base on your exponent must be 2. Those two have to be the same base when you do this. So I could give you, for example, what's the number I have it used? we'll do base 11 of 1 over 121. If I said to you, what is that one going to come out to be? Okay, so what do you know about 121? It's 11 squared, isn't it? Okay, so now I have them both in base 11s, but it has to be up top, can't be on the bottom. So yeah, when I bring that up, that's 11 to the negative 2 power. So now, they both have base 11s. What's the answer? Negative 2. Okay. A logarithm and something written as a base to an exponent, logarithms and exponential functions are inverses. They cancel each other out. So the log takes out the exponential function, and you're left with the negative 2 out of the deal. Okay, what if I gave you log base 6 of the 5th root of 6? What are you going to do with that? You have to ask yourself, how can I rewrite that as 6 to a power? How do you turn roots to powers? Fraction action. So that's a what fraction? Yeah, because technically that's a 1 right now on the 6. So that would be 6 to the 1/5. So therefore, since they both have the same base of 6, your answer is 1/5. So that whole idea of making common bases, making common bases, making common bases, you're going to make common bases till the cows come home. Which is why you may still find your pink sheet helpful if you don't. I bet you're learning a lot of the more common ones here, what they are to a power. All right, challenge problem. Actually, a couple challenge problems. Oops, I don't want 11. I just did 11. Let's do 13. What if I gave you the cubed root of 1 over 169? 169 is 13 to the second power. So I could change that into, okay, that's 13 squared in there. Okay, Jason's bringing it up and making it a negative exponent, so I can buy that. So now I have the cube root of 13 to the negative 2. And then any root, you're going to go, change it to a fraction, because of course we know our rules of exponents like that. So that's going to be 13 to the negative 2/3. So then finally, what's your answer? Because now that I've finally got them to have common bases, my answer is indeed just negative 2/3. So as long as you can work at it using your rules of exponents, you can make it happen. Now, you rarely see this, but I'll show you one. What do you suppose you do if I give you 8 raised to an exponent that has a log in it? It's an exponential function, because it's something to a power, but it's got a log in it with a base of 8. They have common bases. What do you suppose happens? It's 7. Exponential functions and logs cancel each other out. They're inverses. They just wipe each other out. So it's just 7. As long as they've got the same bases, you can almost bet what's going to happen. So now are we having fun yet? And it's weird. You got to work with them a while. You got to practice, because it's just kind of strange until you get this in your head. How you change back and forth, it's a little weird. Okay. There are 2 special logarithms that we like more than any others. These are the 2 most commonly kinds of logs that we ever use. The first kind is called a common log, because they're the most commonly used, or they used to be. I'm not so sure now with calculators that they're as common, but still, your calculator is using this. When your calculator spits out values for you, it's using this. Yes?